record. Presumably it's recording now. Okay, yes. Okay. Someone give me a thumbs up if what you see right now is the exam on my screen. Good? Okay. So what we're going to do is go through this question by question, and we're going to go over the answers, and I'm going to work things out for you guys. So let's look at question number 1. Okay. Okay, so right here, the first thing that we want to note is that mass 2 is bigger than mass 1. So that means that the mass 2 is going to be going down this way, mass 1 is going to be going up this way. If you remember this Atwood machine question, these problems, we always consider the direction of acceleration to be positive, so that we would say that they both have the same acceleration. However, when we are looking at momentum, the direction of the velocity does matter. They have velocities in different directions. So if we count down as positive, which does make sense because again, this one's going to be accelerating down, mass 2 is going to be accelerating down. If we count down as positive, then they each have a velocity of v. So the total momentum is going to be m1 times negative v because it's going up, plus m2v. And so we can see that we factor out a v, and the answer you're going to get is B. So B is the correct answer. Any questions about that? Feel okay about that? Okay. Question 2. When mass 2 has descended a distance h, the potential energy of the system has decreased by what amount? So we need to try to compare the initial and the final potential energies. So if M2 goes down a height h, M1 is going to go up a height h because they're connected. So the change in potential energy then is just going to be mass 1 times g times its increase in elevation, which is h, plus mass 2 times little g times its decrease in elevation, which is going to be negative h. We can factor out a g and an h, and we'll get mass 1 minus mass 2, which is not an answer. However, the question is asking us how much has it decreased by, and so it's like wanting the absolute value of that, which will allow us to flip these basically, because right now we're going to get a negative answer. Mass 2 is bigger than mass 1. And if we flip these, we'll get the positive absolute value of that, because we're wanting to know by what value has it decreased. So question 2 should be A. Any questions about that? We okay? Okay. All right. Question 3. This is a conservation of momentum question. Okay. Don't forget to raise your hand if you have a question. So I can recognize that they both have the same mass, they both have the same velocity, and they're both approaching with this angle of 60 degrees away from the horizontal. So remember that momentum is conserved in each dimension individually, independently, the x dimension and the y dimension. So I can see right away that when they collide, this one is going to have some downward y velocity. This one is going to have the exact same value, a positive y velocity. So I know that those are going to cancel out. Therefore, all the velocity is going to be in the x direction. In other words, in the y dimension, the momentum is conserved. This one has a negative y value, positive y velocity, and those are the exact same value. So those are perfectly going to cancel each other out. After the collision, they should have no y velocity whatsoever. So I'm just worried about the x velocity. This is going to be some simple trig. Here is the velocity. This would be the velocity in the x direction. This is 60 degrees. I'm looking at this top particle up here. So v naught x is going to be v naught times the cosine of 60. And the cosine of 60 is just 1/2. So that's going to be 1/2 times v naught. So they each have an x velocity of 1/2 v naught. So if I conserve momentum in the x direction, I'm going to have initial momentum in the x equals final momentum in the x. So mass of the first object times the x velocity of that object plus the mass of the second object times the x velocity of the second object is going to equal, at the end, it says they collide completely inelastically. If you guys remember, inelastic collisions, perfect inelastic collisions are when the objects stick together. So that's going to give me a final mass of 2m. And I'm trying to solve for this final velocity. I want to know what that is. So this left side of the equation collapses to just m v naught. Divide both sides by 2m. I'm going to get v naught over 2. So the answer to question 3 is B. We feel okay about that? All right. Okay, center of mass question, question 4. Hopefully this one went pretty well for you all. So obviously the X center of mass is going to be right in the middle of these things. So I just need to figure out what the Y center of mass is. It's a uniform wire. So let's say they all have a mass of m. The Y center of mass of this left piece of the wire is going to be L over 2 multiplied by its mass. The Y center of mass of this bottom wire is going to be 0. And the Y center of mass of the top wire is also going to be L over 2 times its mass m, divided by the total mass of the system, which is m plus m plus m. We can say that's 3m. And that's going to get us L over 2m plus L over 2m on the top is just L times m divided by 3m. That's going to be L over 3. So 1/3 of the length is the Y center of mass. And that looks like it's going to be B, right? Because that's a little bit greater than 1/4. So the answer number 4 is B. All right. No hands are being raised, so I'm assuming we're doing good. Okay. If there's a problem, y'all let me know, because I have no idea what you are seeing and hearing right now. Hopefully, what I'm doing. Okay. Question 5 and 6 here. This required a little bit of careful reading because we have 2 different collisions going on. So let's read the question carefully. 4 kilogram mass has a speed of 6 meters per second. There's no friction, so there's no impulse. Collides head-on and elastically, so that means energy is perfectly conserved with an identical 4 kilogram mass initially at rest. And then this one collides perfectly inelastically with the third one. So this first question wants to know, what is the final speed of this guy, of this first 4 kilogram mass? There's a really simple way of doing this and a really complicated way of doing this. The complicated way would be to use your 2 equations that you have for perfectly elastic collisions and solve for the final velocities. The simple way is to recognize that whenever you have 2 objects of the same mass colliding perfectly elastically, basically that means that they just switch velocities. So in other words, as this 4 kilogram mass collides with this one, it's a perfectly elastic collision. I don't lose any energy due to friction or anything. The 2 blocks are just going to exchange velocities. So if this one is at rest, after this one collides, it's going to be at rest. So the final speed of this one is going to be 0. So the answer to 5 is A. Okay. Number 6, this one is going to go flying off then with a speed of, oh, Mr. Bilak has a question. Excellent. Mr. Bilak, I'm going to unmute you, my guy. You have been unmuted. What's up? Mr. Bilak? Maybe. He says it's not working. Do you want to type your question? Could I do the complicated way? Yes, let me try to do the complicated way. Yeah, so remember that it's an elastic collision where the energy is, yeah, elastic. Okay, so let me see if I can at least set this up for you. So I know that momentum is conserved. So I'm going to have 4 times 6 plus 0 has got to equal, let me call this one block 1 and this one block 2 or something like that. So the mass of block 1 times the final velocity of block 1 plus the mass of block 2 times the final velocity of block 2. So here's one equation, and that should be a plus sign. Okay, and then the second equation, oh boy, what is that second equation? It's something like the velocity initial of object 1 minus the initial velocity of object 2 equals the negative of that at the end. Is that right? I think that's correct. So let's see, this would be 6 minus 0 has got to equal negative. Mr. Hassman, yes. The equation is the opposite. Let me consult the sacred text real quick, because it's very likely that I have gotten the equation flipped. Ugh. Sorry guys, give me 1 second. Yeah, so Mr. Hassman, it shouldn't matter which side the negative sign is on. We can move it to whichever side we like. Yeah, so I want to say that's going to work for us. These equations. So Mr. Bilak, I don't know if I want to take the time to do this algebra right now, just because I do want to make sure we get through the whole exam, but you should be able to get the same results, that this first object is going to have a final velocity of 0. The second object will have a final velocity of 6 meters per second from a system of equations using these two equations. This is an elastic collision, and so we have our conservation of momentum equation, and then this is what the conservation of energy equation ends up collapsing down into. Okay, and yeah, I guess from now on we can just try to commit to memory that whenever two objects of the same mass collide perfectly elastically, they do just end up swapping their velocities. Okay, are we all right with that? Okay, neat. Okay, so the final speed of the of these two when they stick together. So once again, we know that this one goes off with a velocity of 6. This is purely conservation of momentum. So I get 4 times 6 has got to equal, they're stuck together, so the final mass is 8 times the final velocity. It's pretty clear that's going to be a final velocity of 3 meters per second. Okay, so the answer to 6 is C. Moving on. Okay, another center of mass problem. This one was a little bit more complicated, but that just means it's more fun, right? So, okay, so this time we have got to figure out the x and the y coordinate of the center of mass. So the x center of mass, let's see. I know that this is uniform. So the first thing I want to do is collapse the 4 pieces of the wire down into their centers. So this one is clearly going to have a center right here at 0, 1. This long piece is going to have its center of mass right here in its geometric center 1, 0. This piece over here is going to be 2, 1. And the coordinate of this one, its center of mass is going to be right here, and that's going to be at 1.5, 2. And please note that this one is going to end up having half the mass as the others because it's half as long as the others. I could write this long thing with density to prove that, but I really don't want to take the time to do that. I can just recognize that this is uniform. Each of these pieces are 2 units long. This one is 1 unit long. So it's going to have half the mass, of course. So the x center of mass, I just need to go multiply the x coordinates of each piece by their masses. What's up, Henry?
When will you get my when will you get my ready?
Give me about 40 more minutes, okay, dude? Thanks, mister. He's excited to do his math assignment, so. Okay, so the x center of mass of the first piece is, of course, 0. It has a mass of m. And the x coordinate of this bottom piece is, of course, a 1. Its mass is m. The second piece has its x at 2. You're right, Mr. Davis. And then the half piece up here has its x center of mass at 1.5, which I'm going to call 3/2. And it has a mass of m/2, right? And then I need to divide all of that by the total mass, which would be m plus m plus m plus half m. So what is that? 3.5 m. There's probably a way to write that in fraction form. So let's simplify this down. On the top, I'm going to get m plus 2m. So that's going to be 3m plus 3/2 times m/2, which is going to be 3m/4. Anyway, and then I'm going to divide that by 3.5m. And you guys can do the math of that. But the x coordinate, you end up getting 15 divided by 14, 15/14. So that leaves us with options A or option C. And we could maybe guess if we're running out of time. Remember, we always want to think about time on these exams. You're only going to have 1.5 minutes per multiple choice question. That's assuming that you don't want any time at the end to go back and check. So 1.5 minutes per multiple choice question about.
Daddy,
Yes, sir.
there's a plant I want to plant too in the spring.
There's a plant you want to plant in the spring? What is it?
So I got this from my apple.
You want to plant that?
I want to plant it.
That's a great idea. Go save it. Go put it on the kitchen counter, and we can find a place to plant it later. Okay. Where were we? We were trying to decide if A or C is the better option. Well, I know that most of the mass is going to be located towards the bottom, right? So 6/7 is going to be like right here, and 8/7 is going to be like right here. So we know just by glancing at this that most of the mass is on the bottom because that longer full piece is on the bottom. So right away, we can get an answer of A without even having to work that out. Now, of course, you could work out the y center of mass if you wanted to take the time to do that. That's going to be the y coordinate of this first piece over here, which is 1 times m, plus the y coordinate of the center of mass of this bottom piece, which is 0, plus the y coordinate of this piece, which is 1m, plus the y coordinate of this piece, which is 2. And don't forget that it only has a mass of half m, so m over 2 divided by the total mass of 3.5 m, you will get 6 over 7. So the answer to 7 is A. All right? How are we feeling so far? You guys with me? Someone give me a thumbs up or something to make me feel good about myself. Oh, thanks, Mr. Spain. Okay, let's keep going. So another conservation of momentum problem. I couldn't see her, okay? I can only see 4 of you for some reason right now. All right. Blah, blah, blah. Let me read this. Best represents the motion of sphere y after the collision. So first of all, we can get rid of B. Well, we can get rid of A and B. Those are crappy answers. No, Miss Scott, don't be sad. I couldn't see your little thing. I'm so sorry. Um, A and B are crappy answers because I know that the y momentum at the beginning was 0. This thing had no y momentum at the beginning. It was all in the x direction. So the y momentum at the end has to be 0. In other words, this one has some positive y velocity. So sphere y has got to end up with a negative y velocity. So I know right away it's got to be C, D, or E. Let's see. I know that the y momentum at the beginning was 0. So that's got to equal the final y momentum. And looks like the final y momentum is going to be, they both have the same mass. So the mass of sphere x times sphere x's y velocity, which is going to be 6 times the sine of 53. And I'm going to add to that m times the velocity final in the y direction of sphere y. And so we can easily now rearrange this and solve for that final velocity of in the y direction of sphere y. We could also do the x direction. We know that that the mass times 10, all of its velocity was in the x direction in the beginning, has got to equal sphere x's momentum in the x direction, m times 6 cosine of 53, plus sphere y's m VFX. Either way you do it, you're going to, through the trig of the thing, end up getting answer D. Answer D, that combination of 8 meters per second at 37 degrees gives us the y and the x velocities that we need. Question, Mr. Davis? Oh, you just want a summary of the answers. Let's see if that's correct. B, A, B, B, A, C, A, D. Yes. It is cool. Okay. Let us proceed. Ooh, this one was super fun. All right. So we get our big balloon of mass m. Hanging from it is a ladder. This is a scenario I personally encounter in my everyday life. I don't know about you guys. It's a rope ladder, so we're assuming the rope ladder has insignificant mass. And then we have a person whose mass is lowercase m, mass is less than the mass of the balloon, begins to climb the ladder at a uniform speed of v relative to the ground. How does the balloon move relative to the ground? So you can think about this in terms of forces, or you can think about this in terms of momentum. In order to move himself up the ladder, the person has got to be pulling down. He has to be pushing down on the ladder, on the rope ladder, so that the rope ladder will push him up. And he's doing that with a certain force to give him this velocity of v. Well, he's pushing down on the rope ladder, and therefore on the balloon, whose mass is big M. To pull himself up, he has to push down, Newton's third law. So he pushes down, the ladder pushes him up. Well, he's pushing down with that force, but the balloon has a bigger mass. So the balloon is going to be accelerating downward, but with less acceleration. So therefore, the balloon is going to be getting a smaller velocity. So the answer to 9 has got to be D. Here's another way of thinking about that. We can also say our center of mass idea. Here's my balloon, here's the ladder with the person on it, and I can say that there are no significant external forces. The balloon is floating motionless in the air, so I know that yes, there's gravity, but gravity is being counteracted by air resistance in this case. So I know right away that there's no net external force. That means no impulse. That means that my center of mass has to keep doing what it was always doing. It was motionless. So the center of mass cannot move. So I know that the velocity of the center of mass has got to remain 0. That's one thing to think about. If I were to write an equation for what the center of mass is, it's going to be M, big M, times the y coordinate of the balloon plus little m times the y coordinate of the man divided by big M plus little m. And if instead of looking at their y coordinates, I looked at their y velocities, then I can say this. I can change this to velocity of center of mass. I can plug in their velocities here and the equation works. So the velocity in the y direction of the balloon plus the velocity in the y direction of the man. And I can rearrange this equation. I know it has to equal 0. So the big M plus little m on the bottom goes away. Sorry, this is kind of shoved in here and kind of getting sloppy, but this basically rearranges to this. Big M, velocity of the balloon, plus little m, velocity of the man has got to equal 0. I can rearrange this and see that the velocity of the balloon is going to be negative and is going to be smaller than the man's velocity because the balloon is more massive. So we could use the center of mass idea. I don't think I emphasized this a lot in class, but just like we can write these equations for the y coordinate or the x coordinate of the center of mass, we can just replace those with velocities and have the exact same center of mass equation. Instead of the coordinate, though, it's going to be the velocity, et cetera, et cetera. Okay. I think in order to get all this done, we're going to have to speed up a little bit. I apologize. So let me try to speed up some. Question 10. Simple conservation of momentum question. It explodes into 2 pieces. So conservation of momentum says that m times v, and it was moving to the right, so that's a positive v, has got to equal the final momenta of the pieces. So my 2/5 mass piece is moving with a speed of v naught over 2 to the left. So I'm going to make this negative. The speed of the other piece has a mass, of course, of 3/5 m, and I want to know what its final velocity is. So I'm just going to rearrange this equation and solve for final velocity. And when you do that for question 10, you should get E as your answer. All right?
Daddy, how much?
Mm-hmm. We got about 30 minutes, buddy. Okay?
Until what?
Until I can go start your math thing. Sound good?
Okay.
All right. Love you, mister. Okay, 11 is a great question. We want to know what direction does the floor provide an impulse? An impulse causes a change in momentum, doesn't it? So how does this object change its momentum? Well, we can see here from the trigonometry that its x velocity does not change because the angle of incident equaled the angle of reflection. So it did not experience a change in its momentum in the x direction, but it did experience a change in its momentum in the y direction, didn't it? Because it was going down and now it's going up. So the answer's got to be E. The vector of the impulse provided by the floor must be pointing directly up. Okay? Question 12. Okay. All right, so there's several ways that we can do this. We can recognize that impulse is defined as the integral of force with respect to time, which is going to be the integral of 2t dt from 0 to 2. You do that, and you're going to get 4 kilograms times meters per second. That is my impulse, and that is a change in momentum. So if my thing began at rest, I can say this: change in momentum is going to equal m times vf minus vi, change in velocity. And I know that my vi was 0, so that's going to equal mvf. And I've just discovered what my change in momentum is, haven't I? That's what the impulse is, of 4. So 4 equals a mass of 3 times vf. Your vf is, of course, going to be 4/3. All right. There is another way of doing it just purely from a forces perspective. And that would look like this. We could say that MA is equal to our net force. M dV dt is equal to 2t. M dV equals 2t dt. And if I integrate both sides, the integral of dv is delta v, a big change in v. So this gets me m delta v equals the integral of 2t dt, which is the exact equation that we just used from an impulse perspective. So Newton's second law was actually derived originally. Newton derived it from this idea of impulse. So they are very closely related, and we can use both perspectives here. Okay, question 13. Maybe. Okay. The momentum of a moving object is given by this, the force causing this motion. So we know that that an impulse is the integral of force with respect to time, and that equals delta p. And I can kind of rearrange that to say that this is true, that F dt equals some little tiny impulse change, and therefore force is defined as the time derivative of momentum, dp dt. You guys need to know this relationship. It's how we get this relationship right here. These two things are synonymous with each other, okay? Another way of getting that is to recognize that a force, according to Newton's second law, causes mass times acceleration, which is m times dv dt, and that mdv can be defined as little change in momentum, right? If we assume that the mass stays constant. So all I need to do is take the time derivative of this momentum expression, and you're going to get, what, 3 kt squared when you take the derivative of kt cubed. So the answer is A. All right. Number 14. Oh boy. I mean, I would love to listen to Spotify right now, but go away. Okay. we looked at a question kind of like this, where you have objects in a system moving relative to each other, but the system's center of mass cannot move relative to an external reference frame. So as the ball is flying through the air after the throw, what has got to happen to the boat? We know it has to move forward. So A, B, or C is correct. Why does it have to move forward? Because if the ball is moving back, its mass is shifting backwards. The center of mass has to stay where it was before. It has to be doing what it was doing previously because there are no external forces. So the center of mass has to remain motionless. That can be true when all these objects move relative to each other. So the ball moves this way, the boat has got to move forward. Here's another way of looking at it through a forces perspective. In order to get the ball to accelerate, the student has to push on the ball to the left. If the student does that, the ball is going to push her to the right, and she's going to push the boat to the right. So the boat is going to move forward. Okay? So the boat has got to move forward. And then after the catch, the ball ends up right here. Is the boat going to move anymore? No, because once the person has caught the ball, there's nothing to make the boat move anymore. There's no forces after he catches it. There is nothing moving, so the boat does not need to move to keep the center of mass in the same location from an external point of view. So the answer is C. These center of mass questions are a little bit tricky, and I think they're best thought through conceptually instead of mathematically. If you try to do the mathematics of the thing, it ends up taking a really long time. Question 15 is a great example of that. So let's look at question 15. So a person is standing on one end of a uniform raft of length L. It's floating motionless on the water. So once again, there are no external forces affecting the thing. The center of mass of the system has got to stay right there from an external point of view. It's like the center of mass is anchored right here. The person can move and the boat can move, but the center of mass of the system from an external point of view cannot move. So if the person moves all the way to the other end of the raft, how does the center of the raft move? How does the raft move? Well, we can really think about this conceptually. There is a way to do it mathematically, but it ends up taking forever. And maybe if we're, when we're back in the classroom, I can take the time to do it mathematically. We can do it mathematically. We did a problem kind of like this in the packet. But if the person were to move perfectly to the center of the raft, then his center of mass would be lined up with the raft's center of mass. The raft's center of mass is here. His center of mass is, of course, centered on him. If he were to move to the left and line up with the raft's center, one second, Mr. Davis, let me finish my explanation and then I will get to your question. Cool. So if he moves to the center of the raft, then he and the center of the raft have their center of masses lined up, and that has got to happen right here. The center of mass of the system cannot change from this external location. So if he moves to the center of the raft is going to have to shift over D so that its center is right there. And if he keeps walking so that his center of mass is now on the other side of the raft is going to have to move an additional distance D to keep the center of mass in the same spot from an external reference frame. So this is the way I thought through it. I kind of broke it up into steps like this. I thought, okay, what happens if he just moves to line up with the center of the raft? Oh, the raft is going to have to shift over D to keep the center of mass located right here. If he keeps walking, the raft is going to have to shift over an additional length D. You can view this symmetrically. If he's located right here and the center of mass is D to the right of the center of the raft, then by the time he moves all the way over here, then the center of the raft is going to be D to the left of the center is going to be d to the right of the center of mass of the system. So it's going to have to shift over 1, 2d. Mr. Davis, let me get to you. Meaning the center of mass will now be located 1 length of d to the left of the center of the raft. That's exactly correct, Mr. Davis, yes. So Mr. Bilek asked, why does the raft need a shift in order to change its center of mass? Okay, so when I say that the center of mass doesn't move, I mean that the center of mass of the system does not move from an external point of view. The objects in the system can move relative to each other, but the center of mass of the whole system cannot move. In other words, as that person walks along the raft is going to be shifting under his feet to keep the center of mass of the whole system lined up with the same reference frame. In other words, oh boy, if the center of my bow tie is the center of mass of the reference of the system from an external point of view, then as the man walks this way, the boat is going to have to shift its center of mass this way to keep the center of mass at that exact same reference point. In other words, whenever the person ends up on this side of the raft, now most of the mass is on this side. So the raft is going to have to shift to the right to keep the center of mass located from an external point of view where it was before. So the raft is going to have to shift to keep the center of mass of the whole system in the same location from an external point of view. Here's another way of looking at it. As the person walks, he's pushing back to the right on the raft. In order for him to move left, the raft has to push him left. How can he make that happen? He's got to push the raft to the right. So of course that raft is going to shift to the right, and it's going to shift to keep the center of mass the same from an external point of view. So the raft's center is going to have to shift d. That's when both of them are lined up, and then an additional length d when the dude ends up on the other end. Do we feel okay about that? Maybe there is a mathematical way of doing it, but I'd much rather get through more of this exam before we look at that. Okay. Okay. All right, let's keep going. I really appreciate you all's patience as I figure all this out. This is a big learning process for everybody. So thank you guys for being patient with me and for showing up this morning. It means a lot. Okay. Question 16. So here's the way I did it. I said, okay, M1 times V1 is equal to M2 times V2 because they have the same momentum. So under what circumstances will object 1 have more kinetic energy? So I want to see what has to be true in order for this statement to be mathematically true. 1/2 M1 V1 squared has got to be greater than 1/2 M2 V2 squared. I can cancel out the 1/2s, and I can rewrite this as this. M1 V1 V1 has got to be greater than M2 V2 V2. And I know that M1 V1 is equal to M2 V2. So object 1 has got to have a greater velocity. It's moving faster, E. Now there are some answers here that just make no sense at all that you could need to eliminate right away. Like answer D doesn't make any sense, so you could eliminate that one. This question was a little bit tricky. It took me a little bit of time to figure it out, but writing it mathematically this way helped. Okay, number 17. Okay, so once again, we can do the exact same thing that we did before, where we say that change in momentum is caused by an impulse. The definition of impulse is the integral of f dt, which is going to be the integral of 1/2, 0.5, t dt from 0 to 4 seconds. And let's see, that gets us 4. That's the change in momentum is 4. And I know that that equals mass times change in velocity. It had a velocity of 0 at time 0. So 4 is going to equal 5 times the final velocity. Your answer is going to be 4/5, which is 0.8. So 17 is B. Please, please, please make sure that you understand this relationship. We've seen it several times. And if you ever forget that relationship, you can once again get it by doing this. Force equals ma, which equals m dv dt. Rearrange and say f dt equals m dv, where m dv is a little tiny change in momentum for an object whose mass is not changing. How do we go from little tiny changes to a large change? Of course, we integrate both sides, and that's where we get a change in momentum is equal to the integral of f dt. Okay, 18 is a conceptual question, yay. So they both are moving with the same speed. This one to the right, this one to the left, and this one is more massive, so it's carrying more momentum. So after the collision, we want to know what are possible velocities. Well, A is out because we know that overall there is a negative x momentum. In other words, the initial momentum is mv minus 2mv. The momentum of this one is positive, the momentum of this one is negative, and it's more massive. So overall, I have a negative momentum in the x direction. That's true for the x direction. For the y direction, my total momentum is 0. So first of all, these two have the same velocity, and this one is moving down, this one's moving up, so this one would be carrying more momentum, and that would correspond to an overall negative y momentum. That cannot be true. Same is true for this one. This object here is carrying a positive x momentum, while this one carries none. And so that would end up with an overall positive y momentum. This one would end up with an overall positive y momentum, which I do not want. So this one is crappy, this one is crappy. Let's see, this one is crappy because while it seems like the y momenta will cancel out, this one has an overall negative x, which I do not want. An overall positive x. I know already that my x momentum needs to be overall negative because the larger object is moving in the negative direction. So C is a crappy answer. And then of course, E is a crappy answer for the same reason. Both these objects would end up with positive momenta in the x direction. So D is the only thing that makes sense. D, I would have my y momenta canceling out and my x momenta adding together to end up with an overall negative. And that's exactly what I want. How are we feeling? Any questions? You guys okay? Okay. Number 19 was fun. Okay, so we can view this in several ways. First of all, I know this arrow is going to stick, and I know it's moving with the initial speed of v. So the speed of the center of mass is given by which of the following expressions? Well, this is just a conservation of momentum situation for inelastic collisions. So I'm going to get big M times 0 plus little m times v naught is going to equal, that's the initial momentum, equals the final momentum. Afterwards, they have a combined velocity of big M plus little m times vf. So rearrange and you'll see that you'll get answer C. Here's another way of looking at it, if we can take the time to do this real quick. I know that before the collision, the center of mass has got to be doing excuse me, I know that before and after the collision, the center of mass of the system has got to be doing what it was always doing. So I know that before the collision, the center of mass had this expression. The velocity of the center of mass is going to be equal to the mass of my first object times its velocity of 0 plus the mass of my second object, m, times its velocity divided by the total mass. This just comes straight from the coordinate center of mass equation. And of course, I can replace the coordinates with velocities. And that has got to be true before the collision and after the collision. So after the collision, I'm going to get big M going with the speed of VF plus little m going with that same speed VF because they are combined, divided by big M plus little m. And you can see that you end up getting the exact same equation. So the answer is C, and we can get there from 2 different ways. All right. Number 20, I'll go through this one quickly. You can see that these objects have the same mass and they have swapped velocities. So I know right away that it's got to be elastic because kinetic energy is conserved. You could go through and actually check whether or not it's elastic. 1/2 mv squared plus 1/2 mv squared, we use the kinetic energy before, repeat that for after, and you can see quite quickly that kinetic energy is conserved. That's the definition of a perfectly elastic collision, right? Okay, number 21 is the one I screwed up on and forgot to put the diagram on the test. So hopefully you all saw my announcement on the Google Classroom and were able to answer the question regardless. This is a fun question. So let's see. I believe that the picture ended up looking like this. Oh boy, here's the floor. Here's point Y. Here's point X. And I know that that is 60 degrees. So the center of mass of this rod is going to be halfway through, which is right here. And I know that that is equal to a distance of L over 2 if the whole thing has length L. So if I remove whatever's supporting it here, it's going to fall under the influence of gravity. So that's an external force. Gravity is an external force to my system. And what does that do? It acts on the center of mass. My object is going to behave as if its center of mass is being affected by the force of gravity. So in other words, I know the center of mass has got to fall straight down to the floor. So after it falls, it's going to look just like this, where the center of mass is going to be right here. And I know that the rod is going to be laying like this with a length of L over 2 right here. So I want to know, how far did Y displace itself? Well, I can use some trigonometry here and solve for this distance. And the cosine of 60 is 1/2. So this distance here is L over 4. But you can see that away from this point, away from where the center of mass falls, that point Y has to end up at L over 2. So it has gone from L over 4 to the right of the floor with respect to the center of mass to L over 2. So that's a shift of L over 4 to the right. So the answer 21 is C. To do this question, you really just had to understand 2 things. You had to understand that you can treat this as a little triangle with a hypotenuse of L over 2, and that you can find this distance right here, L over 4, the distance away from where the center of mass is, horizontally speaking. And you had to recognize that the center of mass is going to fall straight down, just like that. All right. It was a confusing question, but by kind of drawing and manipulating the picture, you could have gotten there. Okay, 22. Simple math question, hopefully. Let's see. So I know that we have this ball, and I want to know what the average force exerted by the racket on the ball. So I can use this expression for change in momentum. That's impulse, right? Because they're asking me about an average force and they give me a time interval over which that force is acting. I know that has got to equal mass times change in velocity. So you plug these things in. Please, please, please be careful with the sign. So F times 0.03 is going to equal 0.06. That's the mass, times delta V is final velocity minus initial velocity. So its final velocity is 10 in the opposite direction of how it was moving originally. So I have to call that negative 10. And originally it was moving 15 to the right. We always want right to be positive. So left negative 10 is negative. Final minus initial, that will allow you to find the size of the force. The answer is E, 50 newtons is what I got. Okay. All right. I'm aware that we're running out of time and are probably not going to get through the whole test today. So if it's all right with you all, we'll try to get through as much as we can by like 9:20ish, and then we may just have to pick back up with another Zoom meeting tomorrow or Wednesday. I'll try to get a plan together for that. Okay. I apologize. This is taking a little bit longer than I anticipated. Okay, 23 and 24 are really great. Really great graph questions. So the idea is that we release this ball from rest and the air provides significant resistance to it. I want to know which of these graphs shows the magnitude of momentum of the ball. So as the ball is falling, let's say that it's right here, I know that it starts with a velocity of 0. And as time goes on, its velocity is going to be growing due to gravity. But remember, resistance typically is proportional to velocity, isn't it? So if I were to draw free body diagrams for the ball, I know that gravity is going to be greater than resistance. But as time goes on, my force of gravity stays the same. My resistance force grows and grows and grows until it counteracts the force of gravity, in which case I've reached terminal velocity where the acceleration is 0 because the net force is 0 because the forces balance out. So I know that if acceleration is 0, my velocity is going to reach one value, terminal velocity, which means I'm going to have a terminal momentum as well. The answer has got to be D. The only possible answers were A, D, or E, because they all have an initial momentum of 0, because the thing was released from rest. So I know that its initial velocity is 0. And D is the only thing that makes sense, because I know I'm going to be approaching some non-zero final velocity, a terminal velocity. All right, the net force on the ball. This is kind of an old question, but or rather it deals with older ideas from our forces and drag discussions. But I just have told you that the net force is going to be shrinking. It starts being completely gravitational, and then as time goes on, my drag force gets bigger and bigger, while gravity always stays the same. So as my drag force gets bigger and bigger, the net force is the sum of these forces where they're counteracting each other. Eventually, the net force has got to reach a 0, and it should just be shrinking regularly as time goes on, because the drag force is going to be growing regularly as time goes on. In other words, there's no reason why it would come up and then go back down or anything like that. The answer's got to be C. I do start with a net force, a large net force at the beginning, right? And at the beginning, that's when my biggest net force is, because that's when I just have gravity and nothing counteracting it. So C is the one that makes sense there. Okay. All right. So now we get to some free response questions. Yay. So maybe we'll have time to do some of this. 23, Mr. Davis, was D. Did I skip that one? No, I did not. Okay. blah, blah, blah. Okay. A and B should have been really straightforward. These questions I don't recall, but I don't think they come from the College Board. I think I just threw in a simpler question for you guys. So for part A, I want to do a conservation of momentum. PI equals PF. So I know I have this 0.3 kilogram cart moving to the right at 2 meters per second. It collides with a 0.1 kilogram cart moving to the left, so -3. After the collision, the 0.1 kilogram cart is moving to the right with a speed of 1.2. So I want to know how the 0.3 kilogram cart is moving. So here's my equation, conservation of momentum, quite simple. You guys can do the algebra, but your VF there for part A ends up being, I got positive 0.6 meters per second. Is that right? I think that's right. Let me check that real quick because something seems wonky about that. No, that is correct. Okay, so positive 0.6 meters per second. Is it an elastic collision? What we're going to do to check that, we have to see if kinetic energy is conserved. So what I want to do is find the kinetic energy before the collisions. That's going to be 1/2 mv squared plus 1/2 mv squared using these values. And then I want to check the kinetic energy after the collision. 1/2 mv squared plus 1/2 mv squared using these values, where I have to use that final velocity I solved earlier. The final kinetic energy is much smaller than the original kinetic energy. I think for my initial kinetic energy, I got something like 1.05. And for my final kinetic energy, I got 0.126. So you can see that quite a bit of the kinetic energy has gone away. What's up, big boy? I'm almost done. I got about 5 more minutes.
Okay.
Sound good?
What is this?
This is my pen to write and solve a problem. Okay?
But it gets right there.
It does right there. Isn't that cool? Okay, let me finish this up, okay? Thank you, big boy. I love you.
I want to watch it.
Sounds good. Okay, so question 2. This is like the big boy question that is going to be really important for us to talk about, and I guess we'll finish with this one. Hopefully we'll get through it all. So here's the idea. I have this ferry boat is moving to the right, and it reaches this docking bumper, which is connected to this shock absorber. So this velocity versus time graph is of the ferry boat from the time it cuts off its engines to the time it first comes to rest after colliding with the bumper. Right here at time equals 0 is when it hits the bumper. So it hits the bumper with a velocity of 3. So you can see that the collision occurs like right in this time. It's a very, very short collision. And the ferry boat drops its velocity from 3 to 2. Calculate the mass of the bumper. This is a simple conservation of momentum question. PI equals PF. I'm going to do it down here where I have more room. And so I know that the mass of the ferry boat is 2 times 10 to the 5th. And I know that before the collision, it was moving at 3 meters per second. And it's an inelastic collision because I wish it had not told you that. You should be able to figure that out on your own because you're big boys and girls. You know that it's basically going to stick to the docking bumper. They're going to become like one object. So that total mass then is going to be 2 times 10 to the 5th plus m2, the mass of the docking bumper, times their common final velocity, which is 2. So you should be able to solve using some simple algebra for that mass 2, and you get 1 times 10 to the 5th kilograms, of course. All right, that should make some good sense to everybody. Okay, let me erase that. Okay, so after colliding, the ferry boat and bumper move with the speed given by this expression. So this is an equation for their common speed. Although the boat never comes precisely to rest, it travels only a finite distance. Calculate that distance. So you guys should know how I can get from velocity to displacement. I'm going to do this right down here. Of course, we know that delta x is, nope, excuse me. I know that v is dx dt. I can rearrange this to say that, yeah, I should have erased that, huh?
Yeah, erase it.
It's fine, dude.
No, I won't.
Henry,
It has to be erased.
let me work, please. I know that v dt equals dx. If I integrate both sides, I'll get, instead of having a dx, I'll get a big change in x. So all I have to do is integrate velocity with respect to time. And I actually want to get an actual distance. So what are my bounds going to be? Well, you can see that as time goes on, you can see from the graph or from the equation, the velocity approaches zero, but never truly becomes zero. That's what it's saying here. So I'm going to do this. I'm going to say that delta x is going to equal the integral of 2e to the negative 4t dt. And my bounds are going to be from time 0 to infinity, basically. We have not practiced a lot of these integrals with e, but you guys should know how to do them. You can do a quick u sub. You really don't have to do a u sub, but that ends up becoming this. Negative 2 over 4e to the negative 4t, and I'm going to evaluate that from 0 to infinity. And you guys should be able to do that evaluation. Whenever t is 0, this e term becomes a 1. Whenever t is infinity, this e term becomes a 0. And so we end up getting a 1/2. So half a meter. All that work for half a meter. So that's the correct answer. All right, let's do part C, and this will be the last thing that we do. Are there any questions so far? Everyone's feeling okay, hopefully. All right.
What if they have a question at their house?
They can hit a button and it'll tell me that they raised their hand. Isn't that funny? Okay. While the ferry boat was slowed by water resistance before hitting the bumper, so that's like over here. I'm not worried about the bumper anymore. Its speed was given by this. Find an expression for the retarding force of the water on the boat as a function of speed. So I'm going to kind of rewrite this. And let's see what I can. Well, actually, I'm gonna I'm gonna rewrite this to solve for velocity. So if I rearrange this to solve for velocity, I will get velocity equals 1 over all of this crap, or 1/3 plus beta times time to the negative first power. That's how I can say 1 over all of this is velocity. How does that relate to a force? You guys should be used to this by now. Forces cause acceleration, and acceleration is the time derivative of velocity. So if I want to find the force, all I need to do is take the derivative of velocity with respect to time. So I need to take the derivative of this. And to do that, I'm going to use the chain rule, derivative of the outer, retain the inner, times the derivative of the inner function, and multiply it by the mass. So when I do that, I'm going to get this, negative m. How's that granola bar looking? Good, I'm so glad. I'm almost done, Dimple. Okay, so here's what I get at the very end. Okay, and how are we going to put this in terms of speed? We want it as a function of speed, and right now I have it as a function of time. So what I recognize is that, well, velocity was this to the negative 1, and I have that exact same thing raised to the negative 2. That's another way of saying velocity squared, isn't it? So my final answer is going to be negative m beta velocity squared. There could be another calculusy way of getting it in terms of velocity and not time before, but I don't actually know if there is a good way of doing that. You think so? So you kind of had her.
They heard what I was saying.
They do hear what you said. So you had to get to this point and then recognize, hey, dude, that's very, very loud and distracting. You had to recognize that this is just the same thing as velocity raised to the second power. Because velocity is this term raised to the negative first, and here I have it raised to the negative second. All right, my dude. So let's see. Oh no, we didn't get to question 3. We have about 5 minutes. Are you guys good if I start question 3 real quick? I just want to get through as much of it as I can. Okay, Mr. Bilek says sure. So we're gonna go ahead and try to do question 3. All right.
I want them to hear what you're saying.
Hey, both, dude. Hey. If you want to be here, you gotta be perfectly silent. Okay. Okay. So let's do this last one. All right. So 3A, find the speed when a mass of coal has been transferred. So this one is a little bit trickier than the ones that we did in class because this thing has a constant force supplying an impulse. So what I did to start question 3 was I said, all right, the initial momentum plus an impulse is going to equal the final momentum. And the final momentum is going to help me find the final speed. The initial momentum, it started from rest. So I'm going to say that's m naught v naught plus the, oh, he is waiting, isn't he?
Who?
What a guy. Okay.
Who's
Hi, Mr. Kessler. We are just finishing.
Who are you talking to?
One of my students. But okay. Okay. So the impulse, the force is constant. So impulse is force times time, and that's going to be equal to the final momentum is going to be the mass, but the mass is changing. So that's going to be m naught plus whatever mass has been added. Henry Ames. And you have two options here. You can call that MC because they wanted this whenever a mass MC has been added. So you can just say, all right, the final mass is going to be the original mass plus the added mass times the final velocity. And all you have to do is rearrange this for the final velocity. Or you can say, well, wait a second, the mass of coal that's being added, it's being added at a constant rate B. So that rate times time is going to be the mass of coal that was added. However you look at it, your answer is going to be this. The velocity is going to be force times time over m naught plus either mc or bt. I wanted everything in terms of time in my answer, so I did that. Okay? Mr. Coleman, let me unmute you. Okay, Mr. Coleman, what is your question?
Can we just leave it in terms of mass or like substitute for the mass of coal?
Yes, yep. So I said that you can leave it just with that MC term.
Okay, and also at the top too with the T. Substitute for mass.
Oh, I see what you're saying. So you put this T in terms of you basically said this, that mass of coal is B times time, and so time has got to be mass of coal over B. Is that what you did?
Yes.
Yep, that's perfectly fine.
Okay.
Yep, great question. Yeah, because they are asking you explicitly about when that mass of coal MC has been added. So I guess we want that to be an input, don't we? Yeah, that makes sense to me. All right. Okay, I do not have time to get into part B here, but if you guys can remind me, I think we're scheduled to have a Zoom conference on Wednesday as well. So real quick before you guys go, once again, thank you all for your time and your patience. I know that this is kind of wacky, but hopefully this was helpful. My only goal in all of this is to help you guys get ready for the AP exam. So these review sessions over these tests that you're taking are one of the most helpful things we can do. So thank you all for your time and for your patience as I figure this out. and as I figure out how to get my kiddos' needs met at the same time. And tomorrow I'm going to have uploaded a video, an introductory video of our next unit. I do have to go on and start a new unit tomorrow. I know that's a little bit unfortunate before spring break, but we are a bit behind and we have to keep moving forward so that we're ready to take the AP exam. So tomorrow I will be uploading a video over Unit 5. You all need to watch it. I'm going to have you take notes and work example problems with me. As a homework assignment, you're going to have to upload a picture of those notes. So just be looking for that tomorrow morning. I'll try to get it uploaded by 9 or by 8 in the morning. I really don't know if I'll be able to. If it comes a little bit later, I'm sorry about that. But that'll be your assignment tomorrow. And then Wednesday, we're scheduled to have another one of these Zoom meetings, if that's all right with y'all, where we just go over some questions and example problems from our new unit all together. All right, so I will see you guys on Wednesday, same time, 8 a.m. If you all need anything at all, please do not hesitate to contact me, and make sure you're washing your hands. Don't leave your freaking houses, okay? We need to be distancing ourselves from everyone else as much as we possibly can in order to get the nice little exponential growth curve of coronavirus to flatten out, so that our doctors and nurses have an actual chance at helping the population. So yes, we should be mandatory quarantining. I completely agree, Mr. Davis. Anyway, if y'all need anything at all, let me know, and you guys have a great rest of your day, and I'll see you all later.